Alright, welcome back guys. We are getting back into our video notes now. It's been a while, so we're starting our next unit, Unit 3. So I do want you to make sure that you're keeping all your notes in the same place. So I'll have you get a clean sheet of paper out, and I want you to label at the top, before we do the kind of the name for today's lesson, I want you to label this unit. So at the top of a blank sheet of paper, just need to put Unit 3. And we kind of mentioned this a little bit earlier, but this unit is going to be called Logic and Reason. Unit 3, Logic and Reason, is what I want you to label at the top of a paper. Okay? And like we mentioned before, we're shifting a little bit now. We're getting back to some of the main ideas with geometry. And specifically, we want to practice our logic and reasoning skills because we're going to have a lot of proofs in this class. We're going to have to be able to explain each step of a problem that we do. And we'll talk about proofs here later in the unit. But for today, we're just getting into the basics of this kind of thinking. So we're not going to see as many math examples as we usually do, which might be some good news for some of you guys and bad news for some of you, depending on how you feel. But this is just a little bit of a shift. Okay, so for today, label is going to be 3.1, Inductive Reasoning and Conjectures. This is either 29th or 30th, depending on when you're watching it. You can add that if you'd like. And then objective for today is we want to be able to make conjectures about patterns and numbers. And then we also want to be able to use counterexamples to disprove some different statements as well. So again, we're more about kind of arguing and reasoning rather than solving in equations and things like that today. Okay, so first definition we're going to write down here together is inductive reasoning. And inductive reasoning is this. It is using details of a situation. Using details of a situation, if I can spell that, situation, to come to a conclusion. Using the details of a situation to come to a conclusion. So all the little things build up to some answer. And we've seen that before when we talked about those different riddles the other day, when we have all these pieces of information and we try to come to some conclusion. What's the answer? Who's the person that did it? So on and so forth. Okay? And we'll be using that in this chapter. Next thing here, kind of going along with that, is a conjecture. A conjecture. And a conjecture is this. It is a statement that is made. A statement that is made using inductive reasoning okay? Conjecture is a statement that is made using inductive reasoning about a pattern. Okay? And this could mean a few different things. So a statement that is made using inductive reasoning about a pattern. So that could be a pattern that you see in a real world, something, if you think of like your daily routine, that would be a pattern that you have, something that you do consistently. You also see this in mathematics where you have a pattern with an actual shape or a diagram or something like that. And you also see this with numbers as well, where you can have a numerical pattern. These numbers are going up by the same thing every single time, or being multiplied by the same thing every single time. So that's the idea that we're going to kind of use as we start to work through some of these patterns today. Okay? So with that in mind, let's practice this a little bit and trying to practice how to make conjectures and statements using inductive reasoning. All right, so first pattern here, you can pause your video if you'd like, and I just want you to write down this first one these 4 different times. Okay, so hopefully you have these written down. The times are 8:30, 9:45, 11 a.m., and then 12:15 p.m. And what it's asking us to do is saying, given this pattern, I want to use inductive reasoning to make conjectures about this. So if I'm looking at 8:30, 9:45, 11 a.m., 12:15, we could ask, what's the pattern? What's happening from each one? Okay, from one to the next. And hopefully we can see this. We're going to make a conjecture about it. Our conjecture is going to be this. We're going to say the time increases by, and then again, what's the pattern? If we notice, it goes up 1 hour and 15 minutes each time. So the time increases by 1 hour and 15 minutes for each step. For each step in the sequence or the pattern. Okay, so that's all a conjecture is. I'm just looking at that and trying to notice what is the pattern that I see here. the time increases by 1 hour and 15 minutes each step that I go. Okay, simple enough. All right, next one here. Okay, I do want you to pause your video and I want you to draw this pattern as well, and then we'll try to come back and figure out what that would be. And you can put those numbers at the bottom as well. Okay, so we have this pattern here. We have this shape that keeps getting bigger and bigger. We kind of add on another square each time, but I want to be more specific. So specifically with the numbers here, we see that's 4, 10, 18, so on and so forth. And those numbers refer to how many little segments there are in this. So with the first square, we see there's 1, 2, 3, 4 segments. Okay, with the second one, we see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then so on and so forth. So that's what those numbers at the bottom mean. And so I'm asking specifically about all those little blue tiles or those blue little segments and asking what is the pattern with those numbers or how many I have in each diagram. So for instance, from 4 to 10, we can try to look at these and see if we can find a pattern here. Okay, well notice from 4 to 10, I added on 6 different segments. So I'm just going to say plus 6 here. Okay, and this is kind of similar to using the rate of change that we've seen in the past with algebra concepts. From 10 to 18, notice I'm adding on 8 each time, right? From 18 to 28, adding on 10, and then 28 to 40 is 12. Okay, so we don't notice, so all these numbers aren't the same, so we can't just say we add on 4 every time or 6 or whatever. But now we can go a little, kind of one step further and say, do we notice a pattern about the number that's being added on each time? So plus 6, plus 8, plus 10, plus 12, so on. And hopefully we can guess this, or we can kind of see this pattern here. Notice each time when I'm looking at the number that I add on, that increases by 2. So plus 2, and plus 2 here. So if I was asked to make a conjecture about this and how I would explain this pattern, what I could say is, we'll say the amount of segments, since the numbers are referring to the little blue segments there, I want you to write this with me. The amount of segments added on, so 6, 8, 10, so on and so forth, increases by 2 for each step. So that is how we would explain that pattern. We're not saying the amount of segments increases by 2, so we're not going 4, 6, 8, 10, so on and so forth. We're saying the amount of segments added on increases. That number that's added on increases by 2 for each step. So first it was 4, then it was 6, then it was 8, and so on and so forth. Okay? So this is what we're kind of looking for. It's pattern recognition. You know, we probably haven't seen this as much in the math that we've been doing recently, because it's been a lot more, for you guys at least, a lot more algebra and just using equations. But pattern recognition is still one of the key things that we want to practice in math. Okay? All right, so moving on to the next one here. Example 2. Now we're getting more specific about patterns, specifically with numerical patterns. So what are some things that I see with mathematical operations? Is there any pattern that I can kind of see here? So I do want you to pause your video. I want you to take a sec, and I just want you to write these 4 different equations that we have here to start. Okay, so hopefully we have these written down. So we look at this, and we're trying to make a conjecture using these patterns here. So we need to ask ourselves, what's similar, what's the same in every single equation, and then what's similar in all their outcomes, all the final answers, or after the equal sign. So for instance, I have 1 plus 3 equals 4, 1 plus 5 equals 6, 3 plus 5 equals 8, and 7 plus 9 equals 16. So notice there's not a specific number that we're adding on each time. You know, 1 plus 3, 1 and 5, 3 and 5, 7 and 9. It's just random numbers there. But is there a pattern between all of those that we're using? Well, notice all the numbers that we're adding together are all going to be odd. So all these numbers that we're adding together are odd. Okay, so that's one thing to notice. And we're adding them together. So what we call that in math is we call that the sum, right? So what we're going to say is we're going to say the sum of 2 odd numbers. Okay, that's part of our pattern. The details about it. I have 2 odd numbers here, so 1 and 3, 3 and 5, so on and so forth. Okay, what about them specifically? So the sum, remember, is our answer, right? What do I get when I add them up? Well, I get 4, I get 6, I get 8, I get 16. And notice again, it's the same kind of thing where it's not specifically it always goes up by this amount, because I'm talking in general. Anytime I add two odd numbers together, what is going to be my answer? Well, in this case, notice all of our answers are even. So the sum of two odd numbers will always be even. Okay, so that's one pattern I could have seen here with these numbers. So with these kinds of patterns, we're not so much focused on how much is it increasing each step, because it's not talking about just one step to the next. We're talking about in general, anytime I add two odd numbers or something like that. Okay. Other patterns that we can see here as well, trying to get a little more complex. I'll have you pause your video and I want you to take a second and I want you to write down these equations for me, and then we'll come back together. Okay, so for part B, we have these here. 5 times 4 is 20, 5 times 8 is 40, 5 times 14 is 70, and then 5 times 22 is 110. So we have these equations. We're trying to figure out what's the pattern here. Well, notice one pattern that we see, something that's similar in all the problems, is we're multiplying 5 by something every single time. Multiplying 5 by something. And specifically that something, if we look at those numbers that we're multiplying it by, if we can try to come up with some pattern for all of these here, notice all of these are even. So we're going to say we're talking specifically about a multiplication problem involving 5 and an even number. And remember, if we're talking about the answer to a multiplication problem, we call that the product. So I'm going to say here, the product of 5 and an even number So this is the details of the piece, right? The product of 5 and an even number will always be and notice if we look at all the answers here, I have 20, 40, 70, and 110. Okay, I'm not so focused on how much they increase each time. I'm more focused on, what's the pattern between all of them. So one thing that we could say, if we were just saying in general, is hopefully you notice they're all even, right? So that's one thing we could say, but I want to be as specific as possible. So they're all even. Another thing, they all end in with a 0, right? That's another piece. And then the last piece here, something else I want you to kind of notice, and a pattern that I kind of started to see as I was learning multiplication, is anytime we have, for instance, if we look at that, other than the number than that 0, if we look at the numbers in front of them, so 2, 4, 7, 11, notice something about how that relates to the even number that you're multiplying by. Notice 4 cut in half is 2, 8 cut in half is 4, 14 cut in half is 7, and then 22 cut in half is 11. So this is obviously a more advanced kind of pattern that you could see, and this is why we're doing it together. Okay, but just want to get your mind in that habit of seeing what are some patterns, what are some things that we can get very specific about when we say these things here. So I'm going to say the product of 5 and an even number will always be half of the even number. Half of the even number, so 4 becomes 2, 8 becomes 4, so on and so forth, with a 0 on the end. With a 0 on the end. Okay? And like I said, this is a little bit more advanced. I didn't throw this problem in because I want you guys to be able to notice these patterns so easily, right? I threw this in because this is a pattern that I saw when I was growing up, and this is something that helped me as I was trying to remember my multiplication, answers or products. So for instance, if you have someone who asks you, what's 5 times 16, well, I can, instead of trying to type that into a calculator, trying to figure that out, I can just try to use this pattern and say, well, I know I just take the even number and cut it in half, so 16 cut in half is 8, and then add a 0. So 5 times 16 is 80. Okay, it's the pattern that we can see as we start to move forward, and hopefully you guys kind of use these as you're growing up a little bit, but if not, we're practicing them a little bit more in this unit. Okay, so that's the first piece here. One other definition that we need to throw in as well is called a counterexample. A counterexample. So I want you to write this down with me here, and this is fairly straightforward. It's kind of what it would sound like. Okay, a counterexample is one example that disproves a statement. Okay, one example that disproves a statement. So we're going to notice we're using all these conjectures, and we have these different statements here. And really when we make them, we say, like for instance on those last ones, we said every time you add two odd numbers together, you're going to get an even number. Okay. A counterexample with that is just one example that breaks the whole thing. Because if I say this is true for every case, if I find one piece where that's wrong, then the whole thing the whole statement is incorrect. It's not true for everything. Okay. So if we want an example for this, well, there's many different things that we could say. Let's just keep it simple. We'll say the Chiefs. I'll just have you write this down. We'll just use a simple example, and you guys can come up with a million of them, obviously. Okay, we'll say the Chiefs are going to go undefeated this year. They're not going to lose a game. Okay, so that's a statement that I can make. A counterexample of that, one thing that would disprove that, is the one loss that they already have. So they're not undefeated because one team already broke that, and that was the Raiders, unfortunately. So we'd say counterexample. If I remember correctly, I believe that was the Raiders. Counterexample would be the Raiders. The Raiders beat us, so now the Chiefs are not undefeated. It's the same thing that holds true for all these statements that we make. We're making a broad statement about here's something that's true for everything. What's one thing that makes that wrong? All right, so example 3 here. This will be our last one for today. I want to say for these given conjectures, I want to find a counterexample to disprove them. So I want you to take a second, I want you to pause your video, and I want you to just write the first one down for right now. Okay? All right, so first one here, we have this. If you live in Manhattan, then you live in Kansas. What could be a counterexample for this? What would be an example where you would live in Manhattan, but you do not live in the state of Kansas? Well, hopefully some of you guys understand this, but there's not just one Manhattan, right? In fact, a counterexample here would be the much more popular Manhattan in New York. Okay, there's New York City that is Manhattan. And so that would be a counterexample. That's saying that statement is not true because I have one reason where it shows it's not. Okay, so that's just one example of a counterexample. All right, second one here, trying to get a little bit more mathematical. Let's say if n is some whole number, so n is just some variable that I chose and it represents a whole number, and we say for any case, then if I had take n squared, so if I multiply it by itself, then that's always going to be greater than n. Okay, so we can test this here a little bit if we need to, because if we want to kind of visualize this. So for instance, if I plug in, let's say 2 squared is greater than 2. Well, 4, that would be 4 is greater than 2. Yep, that checks out. Okay, some other things that we could see as well. Let's say, for instance, 9 or whatever. 9 squared is greater than 9. Well, 9 squared is 81, and 81 is greater than 9. Okay, if we're trying to come up with other things as well, let's try to think more in depth. Okay, what about negative numbers? Because those are also whole numbers. Let's say -5. -5 squared is greater than -5. And again, this is just random numbers I'm picking. There's not specifically reasons why we have any of these. Okay, -5 squared, remember a negative times a negative is a positive. So -5 times -5 is going to be positive 25. And that is greater than -5, so that checks out. So we have to find some number that I could plug in for n here that would make this statement not true. Okay, and there's actually a couple different choices. One of those numbers you might see, if we think about this, could be 0. For instance, if I plug in 0 here, 0 squared is greater than 0. Well, 0 squared, I know it's just times itself, so that's just 0. And 0 is not greater than 0. It just equals itself. So that would not work. So 0 would be one counterexample. Another counterexample as well, if we were looking for another, we could also say the number 1. If we say 1 squared is greater than 1, well, 1 times itself is just going to give me 1 here. And is 1 greater than 1? No, it is not. It's just equal to it. So that would also not work. So final answer here, what are some counterexamples that would work? 0 could be an answer. 1 could be an answer. Okay? So those would be, and I'll kind of separate these here, 2 separate counterexamples that I would take for this answer here. Just looking for numbers that make this statement not true. Okay, so this is the kind of practice that we're getting into more, is being able to, kind of like we did in the riddles, is being able to notice when things don't make sense, or being able to show why something is wrong or why something is right. Okay, this is all that we want to practice in this unit. Okay, so rest of time today, we have to work on the 3.1 exit ticket. If you're in class, you can make sure to grab this from me. I'll be sure to hand that to you. If you're coming in the afternoon, then just feel free to come pick that up when you come into class, and you can work on that and get that done hopefully by the end of today so you don't have any homework, okay? If you have any other questions, as always, feel free to let me know in class. All right, thanks, guys.